Hello and welcome back. It turns out you can also define sequences recursively. So a recursive definition of a sequence is where each term depends on one or more terms before it. So for example, 10, it says write the first four terms of the sequence defined below, and this is a recursive definition of a sequence. Here we're given that the first term is equal to 1, so that's kind of giving away the first term there, it's 1. And then the nth term is defined as the n minus first term plus 2. So to get the nth term, you look one term before it and add 2 to that previous term. So you can think, to get the next term, you want to take the previous term and add 2 to it. This is where the recursive definition part comes in. So let's look at a sub 2. So a sub 2 is going to be, well, when we have an n equals 2 here, we're going to have an a sub n minus 1, that's 2 minus 1, which is 1. So we're going to have a sub 1 plus 2. So this is 1 plus 2, which is 3. A sub 3 would be, well, if you take the subscript of 3 and you subtract 1 from it, you're going to get 2. So a sub 3 is a sub 2 plus 2, which a sub 2 we just got a moment ago, that was equal to 3. So 3 plus 2 is 5. A sub 4, that's going to be a sub 3 plus 2. And thankfully we just a moment ago found a sub 3, it was 5. And so 5 plus 2 gives you 7. So this recursive definition just says that each term is 2 more than the previous term. Now this is, again, not the only way that we can define it. Most of the times in the rest of the packet we've been defining, the rest of the notes, we've been defining sequences using what we can call a closed form to contrast it with this recursive form of defining a sequence. So a closed form, let me write this in gray because it's not really part of the question, this is a sideshow. So a closed form of this sequence might look something like this: 2n minus 1. When n equals 1, you're going to get the first term, which is 1. When n equals 2, you're going to get the second term, which is 3, and so on. In fact, we saw a sequence that looked similar to this. We had like a 1/3, a 1/5, a 1/7. I think they were alternating in our example. And so we saw that it was the 2n that was generating that plus 2 effect. But that would be a closed form. And sometimes closed forms are more useful. You know, you can jump in, you can get any term you want. You can get the 100th term if you want. And you would have 2 times 100 minus 1. That would be 199 would be the 100th term. But with a recursive definition, to figure out the 100th term, you need to know the 99th term. And to figure out the 99th term, you need to know the 98th term. So you have to go all the way back until you get to the first term, which is kind of the first domino that knocks over the sequence, that gets the sequence started. And you need to know all those previous terms before you can get that 100th term. But sometimes it's easier to define things recursively in ways that are hard to define in closed forms. Let's take a look at example 11, where it says, assume that the following sequence converges and find its limit. So here we're given the first term, which is -1. We're given a way to find the next term given the previous term. So notice the difference here between n plus 1 and n is just 1. So if we're looking at the second term, our n would be 1, and so we would stick in an n of 1 here. So for the second term, we would use the first term plus 6 over the first term plus 2. But that's all beside the point here. What we're trying to find is the limit of this sequence, assuming that it converges. Well, let's start by writing that. You know, if it converges, it's got to converge to something. So suppose this limit as n approaches infinity of a sub n is equal to L. If it's going to converge, if it's telling us it's converging, it's got to converge to something. So let's call that something L. It could be 5, it could be who knows what. I was about to say it could be infinity, but then it wouldn't converge. It's some finite number. Well, also, if you take the limit as n approaches infinity of a sub n plus 1, that should be L as well, because still you're just going out farther and farther in the sequence, and that limit should be L. But a sub n plus 1 we can rewrite using the recursive definition as a sub n plus 6 over a sub n plus 2. So the limit as n approaches infinity of a sub n plus 6 over a sub n plus 2, that should be equal to L as well. All right, but using our limit properties, we know that the limit is going to work its way into each of these terms, right? It works its way past the division, past the addition on the top and the bottom, into the a sub n. That looks like a 9 sub n, a sub n. And the limit as n approaches infinity of a sub n, as we mentioned just a moment ago, is L. So it turns into L plus 6 on the top, L plus 2 on the bottom, and L on the right side, just as before. So now we've got this equation that involves L, and we can try to solve this equation for L. We can multiply the L plus 2 over to the right, move all the terms to one side, factor, set each factor to 0, and we get L equals 2 and L equals -3. So it's a little bit weird, like which one is it? If it's going to converge, it can't be going to both of these at the same time, so it's got to just be going approaching one of these L values. And if you look at the sequence, you can quickly figure out which one it can't be. It can't be the L equals -3. Even though the terms a sub 1, that first term, starts off as negative, if you look at the very next term, if you plug in -1 into here, you'll get -1 plus 6, all over -1 plus 2. The top will be +5, the bottom will be +1, so you'll get a positive number for the second term. And as soon as the terms are positive, they're going to stay positive. There's nothing about this that's going to make it negative. There's no subtraction or anything that would make this negative. So after the second term, all the terms are positive. So we can immediately rule out that these terms are approaching a negative number. So you can write all the terms are positive for n greater than or equal to 2. So that narrows it down to this limit right here. So this recursive sequence is approaching this limit of 2. That's what it converges to. And this last part of the notes was just defining a few terms and leading up to this thing called the monotonic sequence theorem. So a sequence is increasing if the terms just keep getting bigger. So if you have a bigger n value and that gives you a bigger sequence term, then if that's always the case for all n, then the sequence is increasing. It's always increasing. The sequence is decreasing if the reverse happens, if the terms keep getting smaller as you keep going farther and farther down the sequence. Now, to combine both of these concepts together, either increasing or decreasing, because it doesn't have to be one or the other, it could just be oscillating or who knows what could be happening. But if you take those two functions that are increasing, functions that are decreasing, and you abstract them, you can call those kinds of functions monotonic. So monotonic means it's either increasing or it's decreasing. Now, I can't really be doing both at the same time, but it's going to be one or the other. So you can think about it, the monotonic meaning like it's going in one direction. It's always going up or it's always going down. You can also talk about the boundedness of sequences. So a sequence is bounded above if there exists a ceiling, basically. So big M is representing a ceiling. So if there exists a big M such that all of the terms are less than or equal to big M for all n. So big M is just like a ceiling, which would be an upper bound. So it would be bounded above. And a sequence is bounded below if there exists a floor, little m, such that all the terms are bigger than or equal to that floor, little m. And then a sequence is bounded if it's bounded from above and below, both. So it has a ceiling and a floor as well. The monotonic sequence theorem says that if you have a sequence that's bounded, so it has a ceiling and it has a floor, and it's monotonic, so that it's either always going up or it's always going down, then that sequence has to converge. Imagine if it was monotonic and increasing, right? Monotonic in the increasing kind of sense. And if it's going to be bounded, then the terms of the sequence are going to have to be getting bigger and bigger and bigger because it's increasing, and there's going to be a ceiling. They can't go beyond a certain point. So eventually they're going to have to start petering out. They're going to have to start leveling out and getting closer and closer to some value that's before the ceiling or possibly on the ceiling itself. Similarly, if the sequence is decreasing, then eventually it's going to get closer and closer to some number either at the floor or before the floor. And so that's what this monotonic sequence theorem is saying. We're not going to make too much use of it in this class, but it's just an interesting theorem to note. And it's worth it to talk about some of these math terminologies that might come up in future classes. Thanks for watching, and see you the next time.